When I was asked to do this presentation and I asked who's the audience, is it the inspectorate? They said no, it's mining guys. So I really don't know what I must tell you that you don't know already. As Peter said this morning, I think everything that I'm going to tell you today we all know. And then the question still is, all right, so why is it not working? My first question that I want to leave you with is, do we really know, or do we think we know? And that is the challenge that I want to challenge everybody here today. Now, there's quite a lot of things to say, so 30 minutes is quite short, but I'm going to keep it short, and I apologize up front if there's certain things that I'm leaving out. But you just can't get everything that you want to cover, and I'm going to take it very low level, because I believe in what Einstein said. He said simplicity is the ultimate of complexity. And sometimes we try to confuse simple things in order to make it seem important, and that is not what we hear today. So the first question is, what changed? I think there was maybe a better photograph, but in the beginning, in the 1700s to the 1900s, we had these miners that was using chisels, and if you look at the points there, we still have percussion, we still have compressed air, we still have demand, we still have burdens and direction, we still have a jumper, a whole flushing, rotation and thrust legs. So what changed? If you look at the evolution, and this is where I think we went wrong, 1930, because in 1889, Atlas Copco developed the first driven compressed air machine. Is the one at the top left. You can see it's almost like on an agro prop. In 1905, they decided, no, this thing is too heavy, they must make it lightweight. And then they made a lightweight machine with pneumatic impact and hand operating rotation. So somebody still rotated by hand. But in 1930, the first lightweight machine drill with percussion and rotation were introduced. And guess what? That's the drill that's still used today in 80% of the operations. Nothing changed from that design. Now that's almost 100 years ago. In 1935, the Swedish caused the problem, because then they developed pioneered the first pusher leg or air leg as we understand it today. And that's where I believe we actually went backwards instead of going forward. And I will explain why. In 1945, the first tungsten carbide was used in bits, so to make the bit last longer. Now the status quo in rock drilling today, in 1960, Professor Hartmann stated that the past 15 years have been rapid advance in the metallurgy of materials for drilling machines and bits, but rock drill itself continued to largely to be an art. And today, still, it's an art. The percussion rock drills still use the 90% of blast holes drilled in hard rock mining, and undergone no major modification. So as much as we speak about mechanization, in South Africa 80% of our production comes still from handheld rock drills. And that makes a major change. So more and more in the recent year investigation in the field have come realize that to understand percussion drilling, do we really understand what percussion drilling is all about? And they must study the basic action of percussion bits penetrating rock, not the performance of commercial rock drills. There are many attendant variables and cannot be isolated and controlled. Now, what does this mean? That's a mouthful, and I will really try to take it apart very simplistically. If we look at a normal drill, you've got the flushing up front that a lot of people ignore, because at this day and age, the faster you penetrate, and we're getting faster and faster at everything that we're doing, but we're looking at the surroundings. Those that can still remember that far back in the Amtar school, you remember you had to test your water pressure and you had to open the tap. This is the height of what the water should be to have the correct flushing. And it was drilled into us, well, into me, it was drilled into me, but does it still count? No, it doesn't. Not at the speeds that we are drilling today. But we're still keeping to the old rules, and we think we're right, but we're actually not, because the life changed, but we haven't changed. The second one is the rotation and the percussion that takes there. And I mean, percussion is the one that is most probably the biggest threat to all of us. But we don't realize that that's the problem. Because if you really go and ask why in a risk assessment, you will realize that at the end of the day you end up with percussion. That's where everything starts. And guess what? 100 years ago, the hammer was also the biggest problem with the most injuries, the percussion portion. Have we got smarter around that? No, we didn't. And then the last thing is actually your thrust force or your feet force. If you really want to make the biggest impact, you need to keep that bit against the face, because the most power you lose when that thing is separated, to just get it next to the face before you really get the energy to transfer. Energy can't bridge empty space. And just taking those things and now making it even more simpler. If we take this whole drilling effect apart, we're looking at jumpers and drill bits. Now, most of us use the forge collar, the rubber collar, with our drill bits and on our rigs and so on. You will see they all use forge collars now, because the rubber collar can't withstand the feet pressures or the pressure on it. It starts slipping, because we're pushing that bit harder and harder to get it into the rock and keep it onto the face. The second thing is the integral bits. You remember the days when the machine driller actually took 2 or 3 drill steels and then he went underground with it and brought it out in the afternoon that it can be resharpened and all that. We've changed that. We made it easier, and we actually went to button bits. That's probably most popular now. It gave us the opportunity to drill faster. We're penetrating faster. But we didn't adjust water pressure. We're putting more holes into these bits to get more water through. But it's not the amount of water, it's the pressure that you need, because the faster you cut in front, the faster you must flush. How many shift bosses these days go through a panel and actually look at the grit that comes out of the face? If it looks like beach sand, you regrind. You're wasting time. And I don't know if you, but in Anglo Platinum, the average face time, and we've done a huge study now, is actually 3 hours and 5 minutes. So if I can't drill a 20-meter face in 3 hours and 5 minutes, I'm not going to get that face for the day. So now I add more drillers. Now I put 6 drillers on the face, because now there's a lot of roof bolts and all those things. Now the efficiency goes down. It takes longer. There's more AWOPs. There's more people in the red zone. That's directly between the last line of bolts and the face. Now there's more people in there, and I want to get less people in there, because that's where the fall of ground is more prone to happen. So it's these things that we don't think through. Now, rotation and percussion. This is an area that gets ignored the most by even the OEMs, and at huge frustration for me. Because this is the big thing that decides how fast you drill, how good you drill, and what your penetration speeds are. Now, what does indexing mean? Rotation, you must have a good index, otherwise you don't get good penetration. Now, if I just take the 5 dots there, it's the 5 points on your button bit. Those 5 points hit, and then they make those little indentations. But the indentations cause these small little cracks to take place in that hard rock. Then it pulls back. When the hammer pulls back, it rotates. When it rotates, it must rotate perfectly 50% of the turn between 2 of those dents, so that you can hit it 100% there, because that will give you the biggest chip. The biggest chip means the biggest break. The biggest break means the faster you break the rock, the faster you penetrate, the faster you move. Now with our compressed air machines, the indexing is different for every bar of pressure that you've got underground. Now these machines were designed, and it's one machine for the industry. Those machines were designed at 5 bar. If you're running at 3 bar, you're grinding 80% of the time instead of indexing. But we don't look at these things. Now we say, listen, these fancy huge drill rigs that cost me I don't know how many million rand for a rig, can I change the indexing on this machine? Because I want to control the speed at which I'm drilling. No, you can't do that. It's a standard machine. So really, are we really advancing, or are we just putting the stuff on the table? We know what the solution is, but we do nothing about it. The thrust leg, great innovation. I mean, it's good. But it's effectively controlled by the operator. Now, in previous life of mine, we were mining at 84 centimeters, stoping width average. There's some panels that were running at 74 centimeters stope width. Then you can't sit behind the machine. You actually lie on your back in the machine. You drill across your body like this. Then you can't control with your weight the vector, because the red vector, as you see it there on the screen, is actually the waste energy. Because the force, if you've got 5 bar force on that air leg, you want that 5 bar force behind that bit. You don't want 3 bar behind the bit. You want all 5 bar behind the bit to keep that bit against the face so that you can penetrate at speed. Because if you only got 3 hours, you want to get that hole within less a meter or less than a minute a meter. If you can't get it in less than a minute a meter, then you can't get the shift closed. The blast cycle doesn't close. And then people start taking shortcuts, and I don't have to explain to you what that does to your safety. Direction. Now, we were all trained fearlessly at the 70-degree angle. I can still remember my facilitator years ago ran mines. How do you get 70 degrees? Where is 70 degrees? You sit nicely on your back, your one leg in the direction, 90 degrees to the face. You open your legs that you sit comfortable. The other leg show you where 70 degrees is in you fuck up paint line. Now with women and mining, we can't sit like this anymore, so now we've got a problem. But if I give you each a piece of paper and I draw a straight line and I put them on top, and I say draw a line of 70 degrees and I put it on top of each other, I will see something like this. And I've tested a lot of people that I've trained in the past exactly like that, because 70 degrees is anywhere between here and there. And then we wonder why our faces are askew and out of sequence and why things go wrong and why do we have sockets. It starts here. Where's 70 degrees? Anywhere. 70 degrees from where? But everybody knows where 90 degrees is. That's fairly simple. Now, if you just look at it, in the past, you had to drill 70 degrees. Why did the old timers? They were not stupid. They told us 70 degrees because you needed a free face. Now, if you drill the face, now you see that blue portion, it actually doesn't stick past the first hole. It gives you that free face. But the fuses were running at 99 to 121 seconds per meter. For those that still had to learn law out of their heads, not open book like these days. So, so you heard the shots, you could count them. But that shot actually only took a portion of rock out. Now, if you have a 1 meter stope width and you advance 1 meter, one hole takes half of that out. At the density, you were moving 0.7 tons with each shot. Every shot that goes off. Now we're going into shock tube, and it's 204,000, and I've done a lot of work in the past. 204,000 is the optimum. You go faster, your underground, you get more damage. You go slower, you get even, then you must turn the angle because then you're in free face country. So there was a lot of work that was done to get it to the 204,000 millisecond delay. But you're now moving 150 holes in less time than what you previously moved 1 hole. And if you add up, it's 84 tons that you're now moving in the same equation. It's 120 times more rock that you're moving in the same time period when that shot go off. Now, 84 tons. We all went from timber support in the back area, bulk support to elongate support with jackpots and so on. But imagine you install those things and you take an Oshkosh truck at full speed and you just drive into those things. Can they withstand it? Now, 70 degrees, if you drill 70 degrees, that's what you're doing. You're taking 84 tons in a millisecond and you move it onto that support. Now, most of our fall of ground accidents, I believe, is not just the poor blasting, but now you blast not so well, then you jack this lot up, and then you take the support out, and then you set the trap just for the next guy to move in there, and then the rock falls. And that's what's causing fall of ground. That is what I believe the science is behind it. Now with the millisecond timing, you're getting 40% of your top portion of your face blast clean. I like water jetting, was very prone on water jetting. Unfortunately, where I'm sitting now, we can't water jet. But at a 30-meter face, the top 40% of that panel, I blast for you that you don't even need a water jet to get in there. And that's normally where people need to move in, install support, put snatch blocks and those things in, or sit there to start operating. And you want that place clean so that you create a safe environment, that you don't have to install and take out support. That's something that you don't want. Now, the blast moves in 90 directions of the direction of the hole. So if that's the case, if you drill 90 degrees, it's easier for all the drillers to understand where's 90 degrees. You get maximum advance on your drill effectively, and you move 90 degrees, so you move the rock towards the gully. And 40% of that is already in the gully. That's why your gully can't be a half meter deep, because it's quite a lot of rock that you want to pack in that small space. But those are the small things that I believe makes the biggest impact. Now, if you get a 10 centimeter socket on 70 degrees, and you get the same 10 centimeter socket on 90 degrees, you scored 6 centimeters by doing nothing. Less support that you have to reinstall tomorrow, that I can guarantee you. I've seen it myself. Drillers these days, 3 years ago in Platinum, we had a wake-up call when we visited the underground training center, that the average driller spends 64 days in the training center. And after 64 days of training, he gets passed out, and then tomorrow he reports for duty, and he needs to drill 60 holes a day. But then he effectively drilled one single hole. If you didn't get the first one quite correct, then he might have drilled 2. But that's the most amount of holes that he drilled. But he had spent training, he's now trained. That's why we closed the training centers, and we took one of our old mines that's closed down, and we converted into a Yamtar school. So all our training now, the drillers physically drill and blast like we did as Yamtaris. They produce only when they get to a certain level that we send them out. But one of the areas was for them to collar and to get direction and to get the understanding of the bottom of the hole is actually what's important. This whole director was developed by one of our production managers with the OEM, and we're using these things quite successfully, and they get quite clued up within a month or 2. Then they don't want it anymore, but at least then they know what the basics are. If you know what the template looks like and you've seen the results, at least in their own minds they can understand what the impact is of good and bad drilling. And when you get that done, you actually move forward. You've all seen some of these mock-ups, a lot of training to make them understand where the end of the hole is and what good burden and good spacing is. Flushing, water pressure. Do we have enough water pressure? I don't know what the water pressure is, but a lot of our machines, you can't set the water pressure. On an S26 you can open the tap and close the tap, but is there enough pressure in the pipe behind you, especially when you start mining 5-6 kilometers away? Is the main column that feeds to your stope, is it still big enough? Have you got enough pressure that you can do the flushing, or do you do regrinding? That bit can't hit the solid rock through a lot of grinded stuff in front of him, then he just smash it to try and get it out. One of the biggest failure of the Hilti drills was that they had round steel. The hexagon steel was developed by a few wise old men to make sure that it actually flushed the water so that you can get the grit out of the water. A round steel doesn't do it. And I see too many people, especially in development, that use the steel until it's so thin you can almost see the water tube shining through on the side of the steel. You're getting very little flushing. You might as well buy a new steel and get better penetration and save money somewhere else. The rule of thumb, as I said, doesn't work anymore. And how do we convince the OEMs that we actually want to change the rotation and the flushing on the physical machine so that we can penetrate faster for the condition that we are sitting in? This is also one of the big areas. I think some of the previous presenters talked about it previously, and I've seen a lot of visitors coming And then they walk away and they say, no, yes, they're also going to reduce their bit size and they're going to do this and that. It's a full process. You can't just change one thing. Your hole diameter and your burden is absolutely integrated with one another. Now, the problem is that if you look at penetration speed, the smaller your bit, the faster you penetrate. So everybody wants to go from a 42 mil to a 36 mil. It sounds to be everybody does it, so that's the most favorable thing. But as soon as you start doing that, you must now look at your burdens, because your burdens must now also tie up. Now, they play against each other, but somewhere where they cross, that's where the sweet spot is. Now, for every rock condition, it's different. You need to test it to understand where is that sweet spot, so that you set yourself up, that you get the best explosives or the least amount of explosives for the best blast. And those 2 points, when you get it good, perfect, done, you get the best fragmentation, and I will elaborate a little bit more on what that means. Now, we've also looked at a lot of energy sources. Manpower is one of them, compressed air is another one, hydraulic oils, hydraulic machines, hydropower machines and electric machines. There isn't a bad one, but each one has got its pros and cons that we need to think about. But what they all have in common is the percussion is the big killer. White knuckle disease will come from the physical percussion on the machine itself. Frame cracks, the guys in trackless mining, those big drill booms, those things cost a few million. Where's the problem? It sits in the cracking of the booms and frames. The percussion actually shakes that whole thing apart. The machine vibration fatigue, I don't have to elaborate more on that. But on compressed air itself, we're only using 30% of the energy. Actually gets to the machine, and then you're still losing a lot there. So eventually we're only using about 14 to 20% of the physical electrical energy that we're burning here on surface. Hydraulic oils, a lot of contamination and problems now around hydraulic oils. Hydropower, we've got power packs that we need to have a look at, and then attenuators, that's a massive cost, high maintenance. Once again, I can recharge a big lighter, but I can't recharge a hydropower machine. I must send it out so that they can take it apart, that I can recharge the attenuator. Have you ever heard that in your life? Right? But why? The question is why? Why must I battle with that? Is that a money racket, or is somebody helping to actually change the mining industry? Then electricity, I mean, the Hilti machines, we're prone in developing the Hilti machines. I think it's an excellent idea. It actually couldn't do what we wanted to do because the amount of development that was needed to go in there, nobody wanted to move on that front further. Now, you might ask now, it sounds like we've done nothing. No, we haven't done nothing. Just a few slides, and I've got about 60 of these slides. I've just taken a few. 1978 to 82, this was very favorable. Machine get away from the thrust leg, try to get more feed pressure. Most of you know these, the setup and so on. Still the normal S26 machine. The next one from the 1990s, we changed the round bar to a square bar because a lot of people's hands got in the way, it tilted and it fallen all over, to try and get more stability on the bar and that it doesn't run away from, especially at steeper slopes. 1979 to 2000s, we've got the double boomer running on rails and on wheels and chains and snatch blocks. And some guys, it looks like they're sailing with all the guide ropes that they've got to get this thing to be in position. There was even attempts to put it on wheels and make it even smarter with double booms with much better thrust forces and so on. But every one of these, just look at the machine. It's exactly the same drill machine of 1930 that's on top of this new invention. So have we really made a change? The latest one is hanging wall, suspending it from your supported hanging wall and running with it so that we make it easier for the operator. But this is, you can't drill. For me, drilling and blasting is Siamese twins. The two plays against another. Because when you change something on this one, you're affecting the other one. You need to get, it's like a marriage, you need to get a 50-50 balance there. Otherwise, we all know how difficult it is. But we need to knowledge and advancement on explosives. Now, in explosives, there was huge advantages. Are we actually utilizing those advantages to ourselves? The velocity of detonation is what is very important. Now, as previous presenter explained, you're only using this amount of the total energy. A lot of that goes into gas and a lot of that goes into waste. But what you want is you want a quick pump, you want to break that rock, make so many cracks in it as you can for a very short space of time that it doesn't run away from you, and then you want to release the pressure. So it's a quick knock. We don't want to build up pressure and then break it or crack it to wherever it goes. Now, that's what VOD does, is the speed at which you can get it. Now, you will see here, the bottom line there is ANFO. So ANFO is a lot of waste energy, a lot of gas energy, but very little shock energy, where emulsions is much better, and in water gels is even higher up. So you're talking from 2,400 meters a second up to 5,000 meters a second. And that does influence your fragmentation. Now, as much as everybody wants to drive drilling and explosives, my biggest drive is fragmentation, because it's something, it's not electricity, it's something I can feel, I can see, I can touch. And it doesn't make a difference on the face, it makes a difference right to the end product in the plant. And that's where most of the cost is. So what does it mean in visible terms? Now, this is from a previous mine I worked on, how we actually changed it. We had cameras in on the belt levels, and we monitor these things for 2.5 years. And we managed to move the mine's fragmentation from a 0.75. Now, what 0.75 is sugar and big rocks. You're most probably all used to that. It caused a lot of mud where you've got water jets and so on, and caused mud and water and all those things that you don't like on the one hand, and it caused a lot of big rocks that doesn't go through grizzlies, that doesn't like to stay on belts, and it's lying all over, and nobody tends to break them because they're these nice round boulders that's very difficult to break. Secondary blasting. And then you move it across to something like that, that's a uniformity index of 1.5. What we realized then is that the other benefits that we got is our cleaning went a massive amount faster. Our sweepings were reduced. Our drainage in our ore passes, we haven't had mud rushes anymore, because now it's so coarse that the water tends to drain through the product. Our belts, we didn't climb off belts, we didn't have all the belt maintenance. But the thing that, by surprise, not by design, learned by trial and error, is that we then pushed 15% more capacity through the plant. Now, I just came from one of our bigger mines yesterday, Magalakwena, where we've got a plant capacity of one of the plants for 600,000 tons a month. They were battling to get 480, 500 for years, and 18 months ago we started changing the fragmentation. The last month we done 705,000 through a nameplate capacity of 600,000 ton plant. And I believe it's all coming back to exactly that. You break the rock in front, the crushers doesn't crush anymore. It's just what I call a moving chute now. But you just make sure that nothing goes in there. Now the benefits from that is ginormous, because it's 100,000 tons of metal worth that you get in for exactly the same cost, the same price, same everything. So it might cost you 20 cents, and that's the biggest fight that I have with everybody. It might cost you 20 cents, in the pit, but it saves you rands at the back end on revenue if you can get that sort of, and you get all the benefits from safety and conditions and less dilution. Because if you can control the fragmentation, you can control the velocity of the blast, you can actually, the dimensional compliance is what you then control. And dimensional compliance, you cut it instead of break it, and then you've got a lot of dilution, less support that you need to install. On the people side, I mean, that's the one area that we shouldn't lose sight of. Top and bottom limits. If you're going to drill 90 degrees, you must make sure the gully is double the stope width ahead of you. Because if you bring all that rock and you don't have a free face, you actually blow everything up. You cause increase in energy. So you're actually going backwards instead of forwards, because that stuff, that energy must go somewhere. So you need to create a proper free phase for it. So your shift supervisors need to look at those things. Direction lines. Do you know where 90 degrees is? So that everybody can drill off that 90 degrees. Charging sticks. Very few places these days will ever get into a panel where there's 3 or 4 or 5 Kubela sticks that the guys actually put in for you when you want to see what the drilling direction is and what the depth is. How many supervisors are still checking those basic things? It's just not there anymore. Just do yourself a favor, go and visit the next panel and just ask for 4 Kubela sticks that you can put it in and see what your direction is and see if you find it. Temporary support installation versus marking. If you don't, as I explained, drill 90 degrees and blast 90 degrees, your support is going to be missing. And elongates go through a grizzly, but it doesn't go through a tip and through a box and onto a belt, into a skip, into a cage, into a hopper. It doesn't like that, and that is where we're losing a lot of opportunity. Clear standards, proper training and discipline, and then obviously incentives. If the guy's doing better and they're really performing, what is the benefit to them to really make sure that they deliver a quality blast? Just a few results. On the left-hand side there, this is a 3.7 meter round that we're pulling out Unki in Zimbabwe. It's obviously with drill rigs. But when last have you seen a 3.7 meter round with half-cast barrels? The amount of support that's reduced, the time that it takes to dress the face, to wash it, to prepare it, get it ready, when there's no sockets and so on, it's ginormous in order to make sure that you've got free time in order to close the cycle. I disagree with one of the previous speakers. This is what a rail should look like. But once again, excavation. Is there a proud in the excavation? Is it straight? Can it be equipped to do high-speed development? In the past, we had shock tubes. There's the drilling shock tubes. These type of conditions with good blasting, pyrotechnics, and all the other advantages, you can change very bad conditions very quickly in 3 or 4 blasts. In mechanization, one of the areas is tires and stability on your machines. It's not just the hanging wall, it's also the footwall. How easy it's for LSD, because if an LSD, 8-ton LSD, put that bucket down, it can't dig. Put that bucket down and it drives into the stockpile. Is it like loading on a tar road? It's clean when it's finished. Because any rock that's lying around, any ditch that it goes through, either break your frames, kill your tires, or damaging something that is unsafe. Now, fragmentation, if you talk about fragmentation, if this is the type of fragmentation that you're seeing, and you take that crew and you explain to them the basics that I just explained to you now, and they understand it. In this case, it took about 4 days to train the crew, and their first blast looked like this. Same conditions, from there to there, in one single blast. It's just a few blasts afterwards. Now, if you get that type of fragmentation, for a machine to clean that, for a scraper to clean it, for a water jet to clean it, it is no problem. Then the uniformity index. You look at the uniformity index. Now, what we're liking is size distribution. I want 100 below 300 mils. So we're doing a lot of fragmentation analysis on our blast work. And you need to understand what it is. Now, on this one, it's 96.6% past less than 300 mils. And we demand 300 mils because all our apertures on our boxes, on our chutes, on our grizzlies is 300 mils. So if you can't blast a rock that it can go through there once, you've got deckers, you've got people rolling rocks with their hands, you've got so many other things that rocks rolling off belts and all that. You just create a lot of issues further down the line instead of fixing it right up front. Hanging wall conditions, once again, this is what hanging walls look like. After 3 or 4 blasts, this is what it can look like by just controlling proper blast. You can see the half cast there of where the holes sitting. But you must set up your hole diameter, your burden, your explosives, your VODs, all those things is a package. It must work together. You must understand what it is, and there is no recipe for all. You must find out which one is yours. So the way forward is we need to mechanize, we need to remove the guy from the face. I mean, there is just no means and ways that we're going to get away from that, and better we wake up and understand that this is where the world's going. We need to remove the percussion effect. Even if we remove the person, we've got machines, and those machines becomes more and more electronics. Now, vibration and electronics, you know, it's like water and oil, doesn't mix. Find better energy sources. Is compressed air still the best energy source? I don't think so. Improve fragmentation. Hopefully I've proven to you that fragmentation is your biggest benefit that generates your cost and your revenue, and become more effective and efficient. Now, Mr. Chair, please, I didn't look at your presentation. It's just that, as you said, we align. Now, in conclusion, mining starts with a hole in the face. Good drilling is absolutely important. But for me, the good drilling, the people, it is people, process, and technology. All those things must fit together. You can't just tweak this one and think, okay, now I'm good. You must look at the whole process flow and set everything up. And really intuit. Listen, did I tick all the boxes before you get to the final result? This is Platinum's way, not as fancy and dainty, robotic like what I've seen before. But this is the areas we're going to use dozers and drill rigs that drill 3 holes at a time. Now, like I explained to somebody this morning, you know, you think you solve one problem, then you create 3 others. Because now I've got 1 hole to set up, line up, level it, and get it right, and we find it difficult to do that. Put 3 next to each other and then try it through a hole and see what you get up with there. It's not that easy. You know, it sounds simple, but it's not that easy, and we really need to get our heads around that. I don't know if there are any questions. Thanks a lot for listening.